Welcome to this lecture 28 of groundwater hydrology. So, in this lecture we will continue the incomplete part in the previous lecture, that is on seismic refraction method, followed by gravity method, and magnetic method. So, these three methods come under surface investigation of groundwater. So, then we will move on to subsurface investigation of groundwater, and in that we will start with geophysical methods, and within this the resistivity method. So, these come under subsurface groundwater investigation. So, in the previous lecture we saw the seismic velocity in unsaturated materials, and in this lecture we will continue with the seismic velocity in saturated materials. So, this is under the seismic refraction method, and this is taken from the same source, that is the American Society of Civil Engineers from 1972. So, here the seismic velocity that is in meters per second on a linear scale. I am sorry, it is on a logarithmic scale, 50, 100, 200, 500, followed by 1000, 2000, then 5000, and this is the horizontal scale, and on the vertical scale we represent the different saturated material. And in case of saturated material, the seismic velocity is more than 1000 meters per second, and here, so this is the for topsoil and organic materials. Then followed by loose sand, so this also will have the same range of seismic velocities. greater than 100 and less than 2000. Then silt, also the same range, followed by gravel. So, we are talking of saturated materials. So, this is gravel and followed by tilled clay. So, this compacted tilled clay, it will have a slightly higher so this is tilled compacted clay, and its higher range, it exceeds 2000, then followed by sandstone. It will have the lower range of velocity in the same this one, and it will have the higher range, which is even higher than that for tilled compacted clay. So, this is for sandstone and conglomerate. So, next is shale, tillite and argillite. It will have a higher this one. So, this is shale, tillite and argillite. So, next is limestone and dolomite, for which the lower range of velocity is around 2000 meters and per second. So, this is limestone, dolomite, and higher range slightly less than 5000. And next is weathered, fractured, so this is weathered or fractured rocks. So, in this case the lower range as well as higher range will be much less than this limestone and dolomite. So, now we will move on to the seismic velocity, its variation, of course, which you have shown already, and you have also seen in the previous this one that seismic reflection is used for greater depths up to 1000 meters and refraction used for smaller depths up to just 100 meters or so. So, now, so there is an equation for relating velocity and porosity. So, this velocity is denoted by the letter V and porosity is denoted by the letter alpha. For consolidated formations, with uniform pore distribution, that is these pores are small pores. So, in this case there is an equation which relates the velocity with porosity, that is 1 by V is given by alpha divided by V L plus 1 minus alpha divided by V S. So, this V L is the velocity in liquid saturating the rock, and this V S is the velocity of solid rock matrix. So, this is the relationship, and here, so this spherical wave which emanates from the shock point from shock point. So, expands outwards, and here, say for example, for a horizontal 2 layer case, with depth to water table of h and distance from the shock point to the point on at which direct and reflected wave arise simultaneously. So, this distance S, which is the distance from the point shock point to the point at which direct and reflected waves arrive at the same time or simultaneously. So, in this case, first let us draw the figure, and so this is the ground surface, and here you have the shock point, and the waves expand outwards from the shock point. So, this is the shock point, and so here this is the water table. So, this is at a distance of h below the ground, and here, so this is the time is in 10 milliseconds. So, this is the time in milliseconds. So, this is milliseconds. So, this ms, this is ms indicates milliseconds, and next it is so this is at a distance of 5 and here so this is this represents 10 milliseconds. So, this curve represents 20 milliseconds, and likewise so this represents maybe say 25 milliseconds. So, in this case, so if this V1 is the velocity of the seismic wave, and in the above water table, and V2 is the velocity of seismic wave below the water table. So, V1 is seismic velocity above water table, V2 is seismic velocity below water table. So, in that case, the depth to water table h is related by the equation s by 2 into under square root V2 minus V1 divided by V2 plus V1, and obviously this V2, the seismic velocity below water table, will be higher than the seismic velocity above water table. And here in this case, if we plot the distance time graph. So, this is the distance in meters, and then this is the travel time in milliseconds. So, in this case, it will show two distinct velocities, one above the water table. So, this is the velocity V1, and this is the velocity V2, and this V1 and V2 so both these velocity lines, they intersect at this distance s, and here, so if the intercept of this V2 velocity curve with this, with the vertical axis, so that is Ti. In that case, we can also write one more relationship, that is h is equal to Ti by 2 into the V1 V2 divided by under square root V2 square minus V1 square. So, this is another relationship. So, where this Ti is the intercept on the vertical axis for the higher velocity line, that is the V2 line, which is represents seismic velocity below the water table. So, and now we will consider there is a 3, this is a So, this is a horizontal two layered case, one above water table which is at a depth of h, the other one below water table. So, now we will consider a three layered seismic reflection case. Scenario. So, in which such that this the velocity through the top layer as well as a second layer as well as a third layer. So, they are the velocities through these layers are gradually increasing, and the thickness, the layer thicknesses are so this is the top layer velocity, seismic velocity, this is the middle layer seismic velocity, and this is the bottom layer seismic velocity. And so, these each of these layers, so this the thicknesses are H1, H2 and H3. So, the layer thicknesses are so this is top, middle, bottom. So, this is H1, H2 and then H3. So, in this case, so the so this H1 can be computed using the two layer formula, which was discussed few minutes back, and this so this H2, so this can be computed as half of Ti square and Ti, I am sorry. So, this is Ti2, that is the intercept on the vertical axis, the time intercept on the vertical axis, minus 2 H1 into under square root V3 square minus V1 square divided by V3 into V1 multiplied by V2 V3 divided by under square root V3 square minus V2 square. So, this is the expression for determining the thickness of the middle layer H2 in terms of the velocities V1, V2, V3 as well as the thickness of the top layer as well as the time intercept in this of this this V2 line, I am sorry, the V3 line. So, this Ti2 is the time intercept of V3 line. So, now So, this the field procedure for seismic refraction has been considerably simplified. And so, here in this a small charge, a small dynamite charge is placed in a approximately 1 meter deep hand augured hole which is backfilled, which is filled again. So, the time of travel as well as the travel time is recorded for points 3 to 15 meter apart along the along a line from the shock point, along a line passing through shock point. And here, so now let us discuss about the interpretation of the data. So, this interpretation of the data assumes that the interface is a plane. If interface is not a plane, then there will be a curve, a small curve joining the two velocity lines. Instead of a point. So, here the actual presence of the for estimating actual presence of groundwater supplemental information is required. And so, using this supplemental information regarding unsaturated and saturated zones. So, then we can estimate the presence of groundwater. So, this seismic refraction method when applied can rapidly eliminate the unfavorable areas for test drilling. So, here this it requires trained personnel for operation and interpretation and data interpretation. Therefore, it is applied commonly to map cross sections of alluvial valleys to estimate variations in unconfined aquifer thicknesses So, now let us go to the gravity method. So, in this gravity method, the density variations in earth surface indicate geologic structure. So, this is the principle on which the gravity method is based. and this gravity method is very expensive, since difference in water content so below the ground, below surface, is very small. Therefore, this gravity methods are under special geologic conditions so like large buried valleys so the gross configuration of aquifer can be estimated by gravity methods. So, lastly, we will go to the last method in this surface groundwater investigation, that is the magnetic method. So, this magnetic method it enables magnetic fields, that is the mapping of magnetic fields. So, indirect info related to groundwater like dikes forming aquifer boundaries has been has been obtained satisfactorily with magnetic method. So, this completes the surface investigation of groundwater, and now we will move on to the subsurface groundwater investigation. And we all know that. So, this subsurface groundwater investigation is the only only it can provide. It means the subsurface groundwater investigation, it can provide the detailed information regarding groundwater. And here so the subsurface groundwater investigations are carried out by technical personnel on surface operating the equipment which extend below the ground, below the surface. The equipment as well as its field of application is below the ground. And here, so we will go to the geophysical method which is also known as geophysical logging So, in this geophysical method, so it involves lowering of a sensor or a sensing device in a borehole and recording the physical parameters. Which can interpret this groundwater quality, quantity and movement. Quantity and movement. So, we will move on to this geophysical logs continuously provide info on subsurface conditions which can be correlated from one well to another, and here so this geophysical log for groundwater investigation is less sophisticated as compared to the one used for petroleum exploration or oil exploration or investigation. Now, let us consider the geophysical log in unconsolidated rocks and geophysical log in consolidated rocks. Geophysical log in unconsolidated rocks. In this case, so this is the ground level, and this is the borehole, and here there are various depth ranges. So, in this let us say these are the say 1, maybe 2, 3, 4, 5, 7, 6, 1, 8. So, here this 1 indicates medium grained sand, 2 indicates boulder clay, 3 indicates let us say 3 indicates coarse sand, and the 4th one indicates fine sand, the 5th one indicates silty fine sand, the 6th one indicates, let us say it indicates brown coal, the 7th one let us say it indicates clay, and the 8th one let us say it indicates a clayey silt. And in this case, say this geophysical logs can be used for getting the variation of this one. Say suppose here we are plotting the spontaneous potential, and in this case say this is, let us say, the positive potential is shown on the right side of this vertical line, and negative potential is shown on the left side of the vertical line. And in this case the variation of this the potential suppose this is the variation of the spontaneous potential, and then similarly let us say take the resistivity, the electrical resistivity, and if this electrical resistivity suppose it shows a variation like this. So, this is the variation of the electrical resistivity, and then let us say this is the variation of this gamma ray. So, this is the gamma ray, and suppose this is the and in this case the values increase in this direction, whether it is the electrical resistivity or the this one, and then the same thing can also be done for this caliper. We will discuss each of this separately, and this geophysical log consists of this continuous information from Bison. So, based on this these different properties, we can interpret the formations as well as the groundwater availability in each of these. So, we will continue in the next lecture on this geophysical investigation, as well as we will specifically move on to the resistivity investigation or spontaneous potential investigation and so on. Thank you.